Hello everyone, my name is Rajan Khadka and my research topic is a metric study for solar observer tube with internal and external structures for heat transfer enhancement and temperature leveling using additive manufacturing technology. I was helped by Dr. Bain Su from our mechanical engineering department. So content, first I will be going on to the overview of solar observer and CSP technologies, then the research proposal, then I will be presenting my studies about what I found. So first overview of solar observer, solar energy and CSP technology. Solar energy is one of the rapidly growing technology that is used to make electricity from solar heat. It is a very clean energy, so its demand is growing. It produces zero carbon emission and it has a very few environmental concerns in regards to other energy sources. There are two types we can generate electricity. One is photovoltaics. Here is a sample photovoltaics power plant in Copper Mountain Solar Facility in Nevada. Photovoltaics is the process where solar energy is directly converted into electricity. And the second one is concentrated solar power plants. Here is the picture of concentrated solar power plant. Uh, in concentrated solar power plant, and there are tubes that receive heat energies and that transfer heat energy into mechanical energy and finally converts into electrical energy. So there are four types of CSP technology currently available. The first one is solar tower. The second one is parabolic trough. The third one is linear fresnel, and the fourth one is parabolic dish. Parabolic trough collectors are one of the most widely used um, technology. Globally, it's used by around 95% of CSP installations. Solar tower occupies around 3% of the global CSP installations, but it's growing because of its high capacity of producing electricity. So what is solar tower? So basically a solar tower plant consists of a single tower standing tall between many heliostrats when it's from outside. Uh, the heliostats captures sunlight and reflect it into the central receiver system over here, and the central receiver system has observer tubes that absorbs heat energy and hits the molten salt that will be flowing through it, and the molten salt converts goes through the Rankine cycle and converts the heat energy into mechanical energy, which finally converts it into electrical energy. Here is a sample CSP plant of Spain. It's called Gemma Solar Power Plant. So the schematic of solar observer tubes look like this in a figure. The first one shows the solar observer tube in the solar tower. The black part here is the solar observer tubes. The solar observer tubes are arranged linearly, circularly in a bundle like this as shown in figure 2, and there will be heat transfer fluid flowing through it. The heat transfer fluid can be in direct steam or molten salts or air. So I'm going about the research proposal. So our research proposal, our main proposal of the research was to make Inconel 718 and boron powder to additive manufacture solar observer tubes with internal and external fins to create more efficient solar observer tubes. So here are some of some of our goals that we wanted to obtain from this research. The dimensions of the tube was 1.5 inch outer diameter. We wanted the tube to be 10-meter long. The thickness of the tube will be 1.2 millimeter to 1.6 millimeters. We prefer UTT chloride salt as our heat transfer fluid. operating temperature for a solar tower is generally between 550 degrees centigrade to 720 degrees centigrade. We plan to obtain the thermal efficiency of 75%. So why do we need to mix Inconel and boron? Because it is so because a solar observer tube is presented or to on uniform heat flux as shown in the figure, this figure over here. The part of solar observer tube that faces the heliostats and that directly receives the heat from the heliostats are more hotter than the parts that do not receive heat, and because of this non-uniform heat flux, the solar observer tubes goes to constant expansion and contraction, and which will lead to fatigue and cracks and deformations. But when you mix boron into the Inconel 718, it will increase the mechanical strength of the solar observer tube, and we can obtain higher efficiency, higher aging. So, in this research, my main part was to focus on the material property. Mm, So here is what I found. The first one is thermophysical properties of Inconel 718. It is very important to study the mattress property before doing any research, and the thermophysical properties for Inconel 718 was found. Um, Differential scanning calorimetry was used to measure the specific heat, and it was found as the function of temperature. Here is a formula, and here is a graph that shows that specific heat is the function of temperature. Thermal diffusivity was studied under laser flash method, and also it was also found as a function of temperature, as shown in the graph. But why do we need this as a function of temperature? Because it will help us calculate the thermal conductivity, which is very important parameter when measuring efficiencies in efficiency in the future. Thermal conductivity can be given as the product of thermal diffusivity times density times specific heat. And when we combine the earlier two equations, we get this formulas over here, which is the function of temperature. The calculated value of thermal conductivity for Inconel 718 on various temperature is as shown in figure or table. So since we are mixing boron and Inconel 718, it's very important to notice the formula to calculate the thermal conductivity of mixers, and Lewis gave a formula that will help us calculate the thermal conductivity of a mixture. These are the formulas that I use to calculate the thermal conductivity of boron and Inconel 718 mixture. And using those formulas and using the thermal conductivity of boron to be 27 watt Kelvin per meter, the table shows the data that I obtained at various different temperature with the various weight percent of boron. Specific heat and density are also important parameters that will help in determining the mechanical properties of the solar observer tubes. And for the mixer, a specific heat can be calculated by the formula shown here, and for density it can be calculated using the formula shown here. And the specific heat of Inconel and boron mixer uh, is calculated and tabulated here in the table. The specific capacity of boron was used to 1.02. Density of Inconel and boron mixer. The density of Inconel 718 measured by the push-rod method was found out to be the function of temperature, as this one here it was, and the measured value for density of Inconel 728 is 8170 kilo kg per meter cube. and using the formula above, I found it to be 8183.809, which gives us the error of 0.16%, which is not bad. And for the density of boron, it's 2.37 gram. Combining these two values, we can get mm, the density of inconel and boron mixture at various temperature at various weight percentage, as shown in the table here. Now the next part is to calculate the optical properties. Calculating optical properties is very much important because optical properties helps us to estimate the efficiency, like how much heat is absorbed and how much heat is emitted by the observer tube. Inconel 718 is considered as a gray material, so emissivity is equal to absorptivity. Emissivity depends upon temperature, wavelength, oxidation time, and angle of incident, as shown in the figure here. The figure first shows the emissivity versus wavelength, which at different temperature, and the emissivity depends upon wavelength. The second one shows emissivity versus angle of incident, and the third figure here shows the emissivity to oxidation time. Total hemispherical emissivity. The total hemispherical emissivity of Inconel 718 is identified as a function of temperature. The research done by Green et al. Found that the emissivity of Inconel at is 0.2 at 200 degrees centigrade and 0.33 at 1000 degrees centigrade. This shows that the emissivity is the function of temperature. The emissivity of Inconel 718 also increases with increasing in oxidizing environment. That means that if Inconel 718 tube is put into the vacuum, then its emissivity will be less than its emissivity than when it is used in normal air because of oxidation. So the emissivity versus temperature of Inconel 718 without oxidation. The left picture shows the one without oxidation, and the right one shows in the oxidized environment at various time period. Total hemispherical emissivity. I also studied the total hemispherical emissivity of Inconel 718 by another author. I had to do so because the one done by Green was done in 2000 AD. This one was calculated using ASTM standard C82506 instrument. The values given and are found by this writer is greater by 10% than the green data, and the writer argues that this may be because of the advancement in equipment and measuring technique. From the data she found, I did linear curve fit method and found the formula for emissivity as a function of temperature, and that formula is over here. So recording mechanical properties of mixture of boron and inconel is very important, as it helps us to estimate how our observer tube, what will be the strength of our observer tubes. The addition of boron increases the fracture toughness of Inconel 718. The fracture toughness first increase with increase in concentration, then decrease with increase in concentration. This is shown in the table here, which shows that when the boron is increased from 12 to 60 parts per million, the elastic plastic fracture and fracture toughness are increasing. But when it reaches 100 parts per million, the fracture toughness has gradually decreased. This shows that the first it increases, then decreases. The transgranular fractures were seen in the alloys with higher concentration of boron. So because of the low plastic fracture toughness or fracture toughness, there are cracks seen on the alloy, and the formation of complex borides and like with molybdenum, titanium, chromium, niobium, nickel acts as a potential crack initiation sites and the alveoli the tube starts to crack. Oxidation is one of the very important properties that helps us to know that needs to be considered before manufacturing any observer tubes. Increasing boron concentration would lead to higher oxidation rates because it affects the composition of oxides. At atmospheric temperature, oxygen reacts with boron to give boron oxide. At liquid, the oxide is liquid at 455 to 475 degrees centigrade and vaporizes at 1000 degrees centigrade. The diffusivity of boron in nickel is very high, that is in the order of 3 to 4, and the diffusion of boron towards oxide scale can largely deplete the bulk alloy from boron, degrading the mechanical properties. Some cavities and spots and cracks were seen because of oxidation in the air. Chromium boride, aluminum boride, mm, and nickel chromium borides are formed because of oxidation. Uh, so there was one case that I found when doing literature review that studied the mm, cracks in inconel and boron mixture. In this particular sample, the boron content was only 0.0038% by weight, and a flash oxidation test was performed at ambient static air in a muffled furnace at 1050 degrees centigrade. Before oxidations, the samples were mirror polished. The samples were oxidized for 0.5, 1, and 1.5 minutes. The samples of oxidized samples were observed in JOEL JSM 7800 F prime sealed emission gun scanning electron microscope. When studied under the microscope after the oxidation, dark spots were continuously observed and the spots coincided with the increase in thickness. Here the left image in the triangle part shows the specific oxidation patterns and the dark patterns. That one is the BSE image, but when the same image is looked on, the same pattern is looked under the SE image, and we can see that the bulk, the thickness in that part is little bit bigger than other part. This shows that the surface is uneven and because of oxidation. And remember, we had first surface mirror polish the surface, and the surface is changing now. So the dark spots seen in the previous slide when on done further analysis under EDS, we find that the intergranular phase were modified by the oxidation process. Nickel, molybdenum, chromium borides were seen on those spots, and also niobium and titanium carbodes were seen in that spots, and burst morphologies were seen as seen in figure here. So after doing that, I also calculated or tried to calculate the efficiency of the solar observer tube in the condition. And the efficiency of solar observer tube can be calculated by this formula, which says the efficiency is equals to observability divided by 1 plus total heat loss over divided by total heat absorbed, and total heat loss is given by the total heat loss by convection plus total heat loss by radiation. Total heat absorbed is given by this formula here, and where n is the number of heliostads, q dash is the heat loss from sun, which is taken as 1000 watt per meter square, and area is the area of observer tube that absorbs the heat. To estimate the convection heat loss, we use the basic heat transfer by convection formula. Since we know all the parameters, we will be just finding the coefficient of heat transfer by convection, which is given as this formula over here. Heat transfer by coefficient of convection is equals to heat transfer coefficient of forced convection plus natural convections. And when we know various properties, when you know the both values, we can find the heat transfer coefficient. So it's first the Reynolds number can be calculated by this formula. Then we can calculate the Nusselt number for a raw surface by this formula according to the Reynolds number. For natural convection of heat loss, we can calculate the Nusselt number by this formula over here. And here the GR is the neutron, which is called Grashof number. Grashof number can be calculated by this formula over here. Okay, so estimating radiative heat loss. So after finding heat loss by convection, it's necessary to find heat loss by radiation, and heat loss by radiation can be found by simple formula of radiation, and there's this one over here. And after finding all those terms, we can put that in the formula that I showed here, and the efficiency can be found. And in all those, I have said that wall temperature needs to be found. For that, when we use sweeting method to calculate the outlet temperature of the salt, and which helps us calculate the wall temperature and finally find the efficiency. First we assume, for this we use the sweeting method. First we assume the T out, that is the temperature out, which helps us calculate the heat in the salt. From this we can find the inside wall temperature, then outside wall temperature. From outside wall temperature we can calculate Rayleigh number and natural heat loss by convection. Then after we can also find from all these parameters the radiation heat loss, and the total heat that we have can be found as total heat absorbed minus total heat loss by convection minus total radiation heat loss. And if the heat of the salt is equivalent to heat loss, or total heat after the loss subtraction, then we can say that our temperature of the, the temperature we assumed is correct, and we can use that temperature to find the efficiency of the tube. If not, we can again go and find, we can assume the new temperature and follow the process. So that is all I have for today. Going ahead, I'll be writing MATLAB code, or I am writing MATLAB code to find the efficiency of solar observer tubes using the sweeting method that I showed you earlier. And I will also be doing more literature review on identifications of change in mechanical properties when boron is mixed with Inconel 718, and identify the correct material for printing solar observer tubes. And I will also be studying more optical properties of Inconel 718 and boron to find objectivity and to enhance the performance of solar observer tubes. I have my references over here.